All right, let's get right into it. When you picture quantum computing, you probably imagine scientists all working together, building the future. But what if the reality is actually more like a war? A high-stakes battle between totally different, totally incompatible ideas about how to build these machines.
And to really get what's going on, we're going to use an analogy, because this is basically an old war being fought on a brand new battlefield. I want you to think back to the 1980s home computer wars, right? The Amiga versus the Atari. That exact same clash of philosophies is happening right now with the two biggest approaches to quantum, superconducting chips versus trapped ion systems.
So what's the fight all about? Well, it boils down to one single critical idea: qubit connectivity. That's the ability for any one qubit on a chip to talk directly to any other qubit. And this isn't just a nice-to-have feature. The argument is that this is the single most important strategic difference. It is the high ground where this entire war is going to be won or lost. So let's meet the two sides in this fight, our modern-day Amiga and Atari, each one with a completely different game plan. And what's really interesting here is that the roles are kind of flipped from the 80s. You've got Team Amiga on one side. That's IBM and Google with their superconducting chips. They took the pragmatic route, basically using familiar 2D manufacturing, kind of like printing circuits on a board. It's easier to scale up the number of qubits, but the design is really rigid. And then you have Team Atari, Quantinuum and IonQ with their trapped ion machines. Now this is a way more complex 3D custom chip design, where they're literally moving individual atoms around. It's an engineering nightmare, but it gives them unbelievable flexibility, and this is the key: superior connectivity. So it all comes down to the core bet each side made. Team Amiga bet on what we can call a trivial design, at least from a hardware point of view. Stamping out a 2D grid where qubits can only talk to their next-door neighbors is just way simpler to build up front. Team Atari made the exact opposite bet. They dove headfirst into the non-trivial challenge, this incredibly complex problem of physically shuttling individual ions around. One side decided to make the hardware easy and push all the hard problems onto the software for later. The other decided to tackle the ridiculously hard hardware problems from day one.
And this table just lays out the consequences of those bets perfectly. You can see the huge differences right away. I mean, look at connectivity. Nearest neighbor for the superconducting guys, all-to-all for trapped ions. And then check out this column, mid-circuit measurement, or MCM. It's a yes for most, but you see that hard no for Google? That's not a small thing. That's a game-changing capability that determines what kind of advanced error correction you can even run.
Let's really drill down on those problems. IBM's heavy hex architecture was actually a step backwards. They intentionally made their connectivity worse to try and reduce errors like crosstalk. I mean, just think about that. They sacrificed power for stability. And Google's Sycamore chip, because it doesn't have that mid-circuit measurement, it is physically impossible for it to run the error correction codes you need for a truly useful quantum computer. It's a dead end, strategically speaking.
And all of this leads to the real consequence of that so-called simple design, a huge hidden cost that just keeps adding up. A penalty you pay for lacking connectivity. We're going to call it the connectivity tax.
So what exactly is this tax? Well, it's the massive overhead in your algorithms, in your capabilities, and in your long-term strategy that you're forced to pay just to work around the fact that your qubits can't all talk to each other, and it comes in three parts. First up, there's the algorithmic tax, or the swap tax. So let's say you need to connect two qubits on opposite sides of the chip. On a machine with limited connections, you just can't, so the compiler has to stick in a whole bunch of extra swap gates to basically play hot potato with the quantum state, moving it across the chip step by step. And every single one of those swaps adds complexity and, more importantly, noise. Your one clean operation just turned into a long, noisy mess that basically destroys your calculation.
And this is not just a theory. A recent study showed that just by being clever about how they arrange the algorithm on the chip to reduce these swaps, they could boost the chance of getting the right answer by an average of 138%. That number, 138%, that's the crushing weight of the swap tax in the real world.
The second tax is, honestly, even worse. It's a capability tax. This isn't about making your program slower or noisier. It's about things you flat out cannot do. An entire class of modern, efficient algorithms that rely on measuring a qubit mid-calculation and then changing course. They are, and I'm quoting here, functionally impossible on hardware that's missing mid-circuit measurement. You are completely locked out.
And that brings us to the final and maybe the biggest one, the strategic tax. This is the checkmate number. Because of the clunky, inefficient error correction they're forced to use,
A nearest neighbor machine needs 4 times more physical qubits to build one stable, logical qubit compared to a fully connected machine. 4 times the cost, 4 times the engineering headache, just to get to the same starting line. It's a devastating disadvantage in the long run.
So let's just sum this all up. For basically every important task, whether it's connecting qubits, running modern circuits, or building a fault-tolerant machine, the nearest neighbor approach pays this enormous tax. Meanwhile, the fully connected approach just does it with one simple, native operation. That easy design choice at the beginning ends up costing a fortune down the road. But wait, this war isn't just a two-sided fight. There's another player that's shaking everything up. In our analogy, we'll call it the Acorn Archimedes. This is a powerful classical competitor that is giving both quantum teams a serious run for their money.
Now, I know what you're thinking. This sounds impossible, right? We're always told classical computers just hit a wall at around, 50 qubits? So how on earth can a classical simulator handle problems with tens of thousands of variables? Well, the secret is, it's not really one simulator. It's a whole ecosystem of different tools that work together. For the really messy, general-purpose problems, it uses a brute force method and hits that same wall. But for more structured problems, it switches to a clever compressed format that can handle hundreds of qubits. And then, this is the secret weapon. For classical optimization problems, it uses a completely classical, quantum-inspired solver that can chew through tens of thousands of variables. It's smart. It looks at the problem and picks the right tool for the job.
And here's the real kicker. In a study from 2024, researchers from both IBM and IonQ, that's Team Amiga and Team Atari, they worked together and created a classical algorithm that solved a problem faster than a big, famous quantum experiment. I mean, the quantum hardware companies themselves are proving that for a huge number of problems, classical computers are still winning. So with this architectural war raging, this huge connectivity tax, and a powerful classical competitor in the mix, what does the path to victory even look like? Let's break down the strategic outlook.
You just have to look at IBM's own roadmap. It tells you everything you need to know. If their core design was solid, they'd just be talking about more qubits and better quality. But look at the highlights: higher connectivity, C-couplers, long-range couplers. This entire roadmap is basically a public admission that their first idea was wrong. They're spending years and huge amounts of money trying to bolt on patches to fix a fundamental flaw, a flaw the other side never had to begin with.
And that brings us to the final verdict from our source material. The Amiga camp's choice, it was a practical first move. But the Atari camp, the trapped ion approach, even though it was way harder to build at first, is based on a fundamentally sounder and in the long run more economically viable architecture. By avoiding the connectivity tax from day one, they've put themselves on a much stronger path to building a useful, fault-tolerant quantum computer.
But let's close with one last, kind of provocative thought. We spent all this time analyzing the war between these quantum machines. But for that whole, huge, commercially valuable market of optimization, the stuff that logistics and finance and drug companies actually want to solve, does any of this even matter? If that classical acorn is already king in solving massive problems today, is it possible the quantum war is already irrelevant for that entire market? Something to think about.